53. Carbon dioxide decomposes into CO and O2 at elevated temperatures. What is the equilibrium partial pressure of oxygen in a sample at 1000 degrees Celsius for which the initial pressure of CO2 was 1.15 atm? Okay, so we're dealing with equilibrium here. We're dealing with equilibrium partial pressures. We can't do anything unless we have a balanced equation. But they described it to us. They said that carbon dioxide is going to decompose, so it's going to break down into carbon monoxide, CO plus O2. So let's write that out. Carbon dioxide, CO2, that's a gas. This will decompose, aka break down, into carbon monoxide, CO, that's also a gas, plus O2. And that's also a gas. Now I'm looking here, and I do need to balance the equation. So let's see. I have 3 total oxygens over here. Let's just see what happens if I put a 2 in front of here. So the carbons are now going to be 2 carbons. So I just have to put a 2 in front of here, 2 carbons. And now the oxygens balance. I have a total of 4 oxygen, 2 oxygen, plus 2 oxygen. So we're good to go. All right, so this is my balanced equation. And ultimately, we wanted to find out the equilibrium partial pressure of the oxygen. So partial pressure just means that you're only finding out the pressure of an individualized component in your balanced equation. So we're ultimately solving for the pressure of O2. So that's my ultimate goal, to get that pressure of the O2. But now we're dealing with equilibrium values, right? And if we're trying to solve for an actual pressure, we chances are need to find out what that K value is, right? What's the equilibrium constant that goes with this equation at the certain temperature? Only until we find out what that equilibrium constant is, can we find out the pressure, because then we can write that expression. But they didn't give it to me. So now we have to backtrack. Instead of trying to solve for this, I first have to find out what that K value is, the equilibrium constant. So this is really what I'm trying to solve for. Now, there's only one formula that deals with equilibrium constants and temperature values, right? They gave me a really high temperature of 1000 degrees Celsius. The equation is this one down here. So we're going to use this first equation. And maybe I'll just link this. Maybe I'll just put it over here. So I want to find capital K, that's equilibrium constant. That equals the E button that's on the calculator, all raised to the negative delta G, so Gibbs free energy, divided by R times T. Do we know any variables? Well, let's see. The R value is always going to be a constant number. Since we're talking about energies, right, delta G, Gibbs free energy, the R value is going to be 8.314. Units, if we're using the 8.314, is joules per mole times Kelvin, which means that the delta G is going to be in joules and the temperature is going to be in Kelvin. Now, they did state that we had 1000 degrees Celsius. So right now, the temperature is 1000 degrees Celsius, but that's okay because I can convert that into the Kelvin value, right? And maybe I'll just bring this over a little bit, just so that I have room, and maybe I'll bring this over for the ride. Okay. So, Celsius to Kelvin, plus 273. More specifically, you could plus 273.15 to get a more, accurate answer. So that's what I'll do. So this turns into 1273.15 Kelvin. So I have the R, I have the T, the E is on the calculator. All I just need is that delta G value. But I don't know it. So now we have to backtrack even more, right? We first said, okay, I want to find that equilibrium partial pressure. But I can't do that unless I have a K value. But I can't find the K value unless I have a delta G. So now here is the question mark. Oh my God, question mark after question mark after question mark. I love this question. Anyway, so how are we going to find the delta G? Well, maybe you might say, well, I could just go in the back of the textbook to get the delta G values for all these substances, products minus reactants, and call it a day. However, that's only at room temperature. I love this problem even more. But they gave us 1,000 degrees Celsius. That's not room temperature. If that was, we would be like living in an existing hell. But anyway, it's kind of like this problem. But since this is not at room temperature, I have to find out another way. So, what's another formula that we could link delta G values with temperature values? That's this formula now coming down over here. Delta G equals the whole enthalpy, delta H, minus the temperature times the entropy, the delta S. But the thing is, I don't have entropy and I don't have enthalpy. But those values are fair game to look into the back of the textbook to find out the overall delta H and the overall delta S. And that's exactly what I did. So let's now just rearrange this. So I'm going to pull this up. So here are all my delta H values. So for the carbon dioxide is negative 393.51, carbon monoxide is negative 110.52, and the oxygen is 0. Let's do the same for the S values. So here's all my entropy values now. So we have 213.8 for the carbon dioxide, we have 197.7 for the carbon monoxide, and we have 205.2 for the oxygen. And now I can get rid of this. More space. All right, so let's start with delta H. How am I going to go from these individual substances to find an overall delta H for the whole entire reaction? Well, that's this formula right here. Delta H for a whole entire reaction, Rx that is reaction, is the sum, that's this little symbol. So that just means you just got to add. So the sum of all the products minus the sum of all the reactants. Now keep in mind that for all the values that you found in the back of the book or an appendix value, you will multiply by their coefficients. So I had 2 CO2s. So I will multiply the negative 393.51 times 2. I had 2 COs. So I times that number by not 1, but 2. And I had only 1 O2, so technically I'll times the 0 by 1. I will add the product side, because I need to sum it up. Literally, it's CO plus O2 to get that summed up number. But let's just do the reactants first. So 2 times a negative 393.51, and I get a negative 787.02, and now let's do 2 times negative 110.52, and that is a negative 221.04 for the whole entire products. So let's plug it in. Delta H for the whole entire reaction is products minus reactants. So negative 221.04 minus the negative 787.02. So delta H equals, I'll just put it over here because I need a little bit more room. I love the TI-84 because I could just go up and press enter to grab the whole values. So that minus this number. And I get 565.98. The units here would be kilojoules because the numbers that you multiplied, the coefficients, those are moles. So the moles cancel out. So this is just kilojoules. And we got one component. Now we have to do the same thing for the S's. So we could use the same formula, which is this one, right? But instead of the H's, get rid of the H's and just put S's, right? So delta S for the whole entire reaction would be the sum of the S products minus the sum of the S reactants. Go to the values that you got and multiply them by their coefficients. So I'm going to multiply the 213.8 times 2, the 197.7 times 2, and the 205.2 times 1. Add the two products together, but let's get that reactant value. So 213.8 times 2, 427.6, 2 times 197.7, plus 205.2. I get 600.6. And now I'm ready to do products minus reactant. Delta S for the whole entire reaction is 600.6 minus the reactants, which was 427.6. All right, we're getting somewhere. We're getting somewhere. So I'm going to just grab the values, this minus the 427. Oh yeah, so we get 173. Units for this, remember the moles cancel out. So the back of the textbook is joules per mole times Kelvin. So this would be joules per Kelvin. All right, we have the delta H. We have the delta S. We know that temperature. Now we can solve for delta G. So I'm going to just take this, move it over here, and bada bing, bada boom. Let's find out that delta G. Delta G equals, but wait a minute. Delta H is in kilojoules, delta S is in joules. We need to convert, right? Which one are we going to convert? Convert to kilojoules or convert to joules? We'll ultimately go back to the formula that we're going to use, right? We want to find out that delta G. And remember, the R value said, delta G, you gotta be in joules. So I'm just going to take the kilojoules and convert into joules. Kilojoules to joules times by 1,000. Similarly, take the decimal, move it to the right 3 times. So this would be the same as saying 565,980. So 565,980 joules. And that's the value that I'm going to plug in over here. So 565,980 minus the temperature, which was 1,273.15, times by the delta S, which was 173. Plug that all into the calculator at once, and we will be able to get a delta G value. So 565,980 minus 1,273.15 times 173. And that looks good to me. Press enter. Non-spontaneous, it's a positive value. I'm not going to round because that's not the final answer. But we found one of the question marks that we wanted. Units here would be in joules. All right, 1 question mark down, 2 to go. So now I found out that my delta G value is 345,725.05 joules. I'm going to finally use this formula to find out that equilibrium constant. So K equals E, all raised to the negative, that's in the formula, ratio, or division, right? Delta G, 345,725.05. Divided by those 2 numbers, we have the R value, 8.314. And then we have the temperature, 1,273.15. Let's just bring this down to emphasize that the E button is being raised to all this. So what I would do is I would just get this to being one number. K equals E raised to the negative, grab that whole delta G value, divide by 8.314, then divide again by 1,273.15. Okay, so E raised to the negative 32.66 and more values. I'm not going to round because it's not the final answer, but we're going to finally find the second question mark. We're getting there. Second ln, that's where the E button is. Grab the whole thing. I love the TI-84. And there we go. K equals 6.53, maybe we'll say 6.533 times 10 to the negative 15th. No units for equilibrium constant. Maybe I'll do this in green. But we found out what the equilibrium constant was, the second K value. So now I know that this is whatever that is, right? The 0.533 times 10 to the negative 15th. Okay, so pause the video if you need to, because a lot of this work has to be, unfortunately, gone, because we need more work to find out that partial pressure. So I'm going to erase all the work, all this pretty work. But that's okay. I'm going to erase all the work for the delta H, delta S, delta G. Goodbye. And I think we could strip it down to basically just this K value. That's all that we need. We did all that work to find the equilibrium constant. Isn't that fun? So now, we're going to bring this back. We're still looking for that partial pressure of oxygen, and here is that K value. So maybe I'll just put it down at the bottom here. Okay, beautiful. Now, we have the K value, and they gave us an initial pressure. Equilibrium constants, initial pressures, we're talking ice table. Isn't that fun? So now we're back to equilibrium, right? We're going to say ICE. Now we're finally this is just your regular equilibrium question now. So ICE. Now the only thing that we started with was an initial pressure, right, of CO2 was 1.15 atm. It's in the correct unit. When you're doing ice tables with pressures, it has to be in equilibrium. It has to be in atm, atmospheres. So I'm starting off with 1.15, and they didn't say that I'm starting off with anything here. So 0 and 0. C stands for change, right? If you didn't start with anything, you could only go up from there. So this side would have to be plus, and this side would have to be minus. By how much? I don't know. So we just use our coefficients. This would be minus 2x, this would be plus 2x, and this would be just plus x. Equilibrium is when you just bring them both together. So 1.15 minus 2x is 1.15 minus 2x. 0 plus 2x is just 2x, and 0 plus x is x. These are your values that are going to be in your equilibrium expression, right? With the K value. So, and now maybe I'll just bring this K value up here. That's beautiful. So let's write out the equilibrium expression. Remember, any K value equals concentration of products divided by reactants, right? So in this case, since we're not dealing with concentration, that's kind of just like muscle memory. But we're dealing with pressures. It's going to be pressure of the products divided by pressure of the reactants. So I have that. They're all gases, so they're all involved. So it would be the pressure of CO times by the pressure of the O2. And remember, it's always raised to the coefficients. So there's two COs, so I have to raise that one to the second. There was only one O2, so I don't have to do that. Divided by the pressure of CO2. And that one I have to also square. So there's my expression, right? And maybe what I'll do is I'll just bring this down a little bit, because the K value is going to be the 6.533 times 10 to the negative 15th. The pressure of the carbon monoxide at equilibrium is 2x, O2 is x, and the partial pressure of CO2 is 1.15 minus 2x. So 6.533 times 10 to the negative 15th equals, let's see, I have two parentheses here, one value on the bottom, squared, right? So we have 2x, and that's squared. And then this is just times by x, and this is 1.15 minus 2x, and that's also squared. Now, keep in mind that whenever you see minus x, minus 2x, we try to negate that. Now, how do we justify that? Because this K value is so small, it's 10 to the negative 15th, that means that at equilibrium, you're going to have mostly reactants. But if you started with all reactants and you're left with mostly reactants, this change is not going to be great. which means that I can just say, hey, probably the ending result is so close to 1.15 that I don't even care about the minus 2x. So I'm going to erase it. We could do the 5% rule at the end just to see whether our assumption was correct. Now, let's just simplify, right? The 2x squared, that just means 2x times 2x. 2 times 2 is 4. So that's 4. And I picked up 2 x's, so that's 4x squared. So if I just say that the 2x squared is now 4x squared, I pick up another x. X squared times x is just 4x cubed. So now we have 4x cubed. And now what we can do is we could basically just cross multiply, right? I could take the 6.533 times 10 to the negative 15th, and I can times it with the denominator, right? The 1.15 squared. So let's go for that. So this will all equal 4x to the third equals, I'll do the 1.15 squared first, get that full number, and then I'll times it by 6.533 times 10 to the, I love using the second comma button for scientific notation because then I don't have to use parentheses. And I get this value, 8.639, what is this, 6.6398925 times 10 to the negative 15th. Notice that I'm not rounding because that's not the final answer. Now I'm just going to solve for x. I'm going to divide by 4 on both sides. So that goes bye-bye. I now have x cubed equals, I will take this value and I will divide it by 4. So now I have 2.15997313 times 10 to the negative 15th. And finally, I can do the cube root. Now, similarly, you can just take this value and raise it to the inverse of what a third is, or not a third, but raising it to the 3, which is raising it to the 1/3. Me personally, that's what I like to do because I don't really know where the cube root value is on the calculator. I just always go for that fraction. So this will cancel out, right? And now I'll just have to take this value. So I'll enter that and I'll raise it to the 1 divided by 3. Same thing. I'll pull that out so I could get that big value back there. Do you see how the whole thing is being raised to the 1/3? Or you could find the cube root, but I just like this better. And I get x equals 1.29. Because now I'm rounding, this is the final answer. 1.29 times 10 to the negative 5th ATM. Now, which one are we solving for? I wanted to find out that equilibrium partial pressure of oxygen. So here's the oxygen. Equilibrium was just x. Oh boy. So the pressure of O2 at equilibrium is x, which is 1.29 times 10 to the negative 5th ATM. And we did it. We did it. Oh my gosh, this was a marathon of a question, but it was fun. A lot of math, but if you guys got this concept, you guys got this problem and all the stuff that's in it. We did equilibrium, we did Gibbs free energy, delta H, delta S. Crazy, crazy, crazy problem. But thank you so much. I really hope that this helped. Let me know in the comments. Love talking to you guys. Thank you for being part of this community and spread the word about this channel on YouTube, or, tell your friends, tell your classmates. I know that some teachers use this channel. So if you are a teacher, thank you so much for using this channel. And hey, let's just keep learning out there. All right. Learning is fun. Chemistry is fun. And we also have other subjects on the channel as well. We got physics and math at the moment. So maybe we can help you out with those, with more subjects to come in the future. Let's just keep going. All right. I'll talk to you soon. Bye-bye.